Oh, okay. I think we are going live. Hello, everyone. I'm Shelven from Phala Network, and this is our fourth Tech Talk. And today I'm gonna talking about the security of Intel SGX. I think this is a question of concern to many of our developer and the community members. And okay, today there are about three topics. First, I will introduce some vulnerabilities which can affect SGX. Especially, I will talk about the Spectre and the Meltdown because last time someone just asked about it. And then I will introduce about the side channel attack, which can exploit such vulnerabilities. And at last, I will introduce how Phala design its mechanisms to mitigate such attacks. Okay. First, I will give a brief review of the Intel SGX. Intel SGX provides hardware-based enclaves where your programs can safely execute it in it. And it provides the ability of remote attestation in which you can verify the integrity and the identity of your program. And your program, when your program is executed in the enclave, it's actually physically it stores its state in physically isolated memories. And finally, all the memories are encrypted with special hardwares. So your program state is safe, even if the operating system and the virtual machine manager from your cloud service providers are malicious. Okay. But actually, the SGX is not the silver bullet to all the security problems. And there are some vulnerabilities which is able to affect the SGX. And I think they can be generally divided into two classes. The first class is the program vulnerabilities, the traditional program vulnerabilities inside the enclave. I will not talk about it because it's all about program writing, right? There is hard to promise that we can write perfect programs, which is totally bug free and run it in the enclaves. But we really have some code review mechanism to reduce the vulnerabilities in our programs. Okay, and the second class of the vulnerabilities is the hardware vulnerabilities. And in the SGX cases, I think it's especially it can refer to the CPU based vulnerabilities because all your state is encrypted outside the CPUs, and only CPU is able to see the plain text. Okay, and from the recent research, there are many CPU related vulnerabilities. For example, we will talk about the Spectre and Meltdown today, and also there are other voltage manipulation attacks which try to the attacker try to lower the voltage of the CPUs, and then they can insert some controllable faults into it. But we will not discuss it today, maybe sometime later. Okay, to understand the mechanism of Spectre and the Meltdown, I think we need to first learn some about some special features of the modern CPUs. Okay. And the first question is how the modern CPU executes instructions. A trivial way is that the CPU can execute instructions one by one. For example, it can we have instruction 1, instruction 2, and instruction 3, and the CPU first execute instruction 1, and after that it executes instruction 2, and then instruction 3. And we can say there is no overlapping between the two instructions, so we can say they are executed one by one. But actually, this is especially low efficiency. While an important idea to optimize it is that we can use the pipeline, and the pipeline is first invented by Henry Ford when he tries to manufacturing the car, and also the modern CPUs has borrowed such ideas. And the general idea is that we can divide the execution process of a single instruction into multiple stages. So multiple instructions in CPUs can be executed at the same time. Okay. For example, in this case, we can divide the execution of a single instruction into 3 stages. We say A, B, and C. And now we can say at each time, for example, in this time, actually the CPU is executing 2 instructions at the same time. For example, the instruction instruction 1 is in its B stage, and the instruction 2 is in its A stage. And at this time, there are even 3 instructions are executed in the same time. So the pipelining mechanism can greatly improve the throughput of the CPUs. And the cost, I think, the cost is that there will be overlap between instruction 1, 2, and 3 during the executions. So actually, for example, in the modern CPU of Intel, as far as I know, there are over 12 stages. So actually, in the modern CPU, there is no clear boundaries between the executed instructions. Okay, this is an important features for the vulnerabilities. Okay. So here comes the question: if we try to compactly execute each instructions, how we handle the branches? For example, in this case, during its execution, we cannot foresee which branch the line 3 code will taken. It can take the true branch, or it can take the false branch. So after we have executed the code of line 1, we don't know which other line which the following lines of code to execute. So a trivial solution to this is that we can wait. We can wait the execution of the line 1, and then we get the value of the input variable, and then we know which instructions to execute. But actually, we can do better. For example, we can just making a guess. For example, we just guess that the execution will reach the line 4 code, and then after we have executed it, we can revert if it is otherwise. Okay, but if we guess it's right, then we have the good performance. Okay, this is the cost. So such technology is called speculative execution, and it is widely existed in the modern CPUs. The speculation executive is driven by a special unit called BPU, the branch prediction unit. It's a isolated unit in the CPU, and it's responsible for the branch prediction, and its speculation is based on the execution history. For example, actually there are very complex algorithm behind it, but for simplicity, I will just use a simple model. For example, if all my historical execution just take the true branch, then my prediction units will say, okay, the next run when I reach the line 1 code, I will take the true branches, because from my historical experience, the true branches have the greater possibilities to be taken. Okay, so this is the trick. Actually, the BPU can be trained, and this is what the attackers really do. For example, by controlling the historical execution trace, the attackers can trick the BPUs to think that, okay, the true branch of this conditional statements will always be taken, and so we can trick the CPU to execute some instructions which should not be executed. For example, actually it should take the false branch in the last iteration, but it's based on its historical experience, it takes the true branches, which cause some illegal instructions to be executed. So this is the problem, and this is the root cause of the Spectre. But actually, during our real-world development experience, there is nothing wrong happens outside the CPUs from our observation. This is because such instruction executions just happens inside the CPUs, inside its microarchitecture, and can be not observed outside the CPUs. Because after the CPU finds that, okay, I make the wrong guess, okay, it will try to revert all its executions. But the problem here is that the reversion of the executions is not complete, which means it has some side effects. Also, the side effects just exist inside the CPU microarchitecture. And in a normal way, it cannot be observed outside the CPUs. So actually, we will find some way to read it out. Okay, this is the problem. Okay, here comes the second question. It's about the instruction dependency. For example, there can be data dependency between different instructions. For example, the line 3 code, it checks the value of A. It's dependent on the line 2 because it changed the value of A, right? Similarly, the line 8 code is dependent on the line 7 code. And if the CPU faithfully executes the instruction in such order, it needs to wait because it takes time for the code of line 2 and line 7 to update the value of A. And then the line 3 code will need to wait the finish of the line 2 code. So how to solve this problem? Actually, in the CPU, the solution is that the CPU will automatically reorder the instructions for you. It will analyze the dependency between different variables and reorder it. For example, in such case, there is no dependency between variable A and B. So during the real execution, the CPU will insert such the change of value B after the change of value A. So there is no dependency between these two instructions, so they can be just pipelined. And such technology is called out-of-order execution. This is also prevalent in most of all the modern CPU. And the optimization of out-of-order execution has mainly it has two effects. First, for instructions with no dependencies, it try to interleave such instructions. So your pipeline is full, and the previous instructions, the latter instructions do not need to wait the finish of the previous instructions. And for instructions with dependencies, for example, these two expressions, it's also introduce an optimization about, we say it's about value caching. For example, after the line 7 has updated the value of variable B, it don't need to write back the new value of variable B to the memories. Instead, there is a shortcut to send the temp value of variable B to during the execution of the line 8. So the line 8 can always get the latest value of variable B without need to wait it to return to the memory and then read it out again. So this is another effect, and this caused the problem. The shortage here is that after introducing the data cache for acceleration, the CPU can read privileged data unexpectedly. And of course, just like the previous speculation execution, the CPU will try to roll back the data, but also it leaves some side effects, and we can use some special technical to read such privileged data. To put it together, these two important optimization in the modern CPU cause the problem. The first is the speculative execution, and after we train the BPU of in the CPU, we can make the CPU to execute some instructions which should not be executed, and this causes the Spectre problem of vulnerabilities. And then another feature is the out-of-order execution, and in it we can trick the CPU to read some privileged data which shall not be read, and this caused the problem of meltdown. Okay, we can now use this is the code snippet which should be used by the attacker. And now we can understand about half of it. I will not give the example of Spectre here because the Spectre is a general purpose attack method and vulnerabilities, and we use the Meltdown. Why the Meltdown is named at Meltdown? Because I think the Meltdown is just melt down the war between the user and kernel space. Because, for example, in the operating system like Windows or Ubuntu or other Linux-based distributions, the system can be divided into two spaces: the user space and the kernel space. And the kernel space is the privileged space, and it holds many important information like the data, your memory data addressing, and the others, and many security critical data. And its data should not be read by the user space applications. But the meltdown vulnerabilities can crack such isolation. For example, in this case, the RCX, the register RCX, it holds a kernel address. And actually, this the value in this address should not be read by the user space applications. So if we try to execute the line 3 code of the assembly, actually it will panic because the kernel will detect, oh, your user space applications try to read some data from the kernel address. But actually, since we have the out of order execution, we have here, so there is possibility that the code in the line 4 and line 5 will be executed, even if the line 3 code will panic. So this caused actually the value of the kernel address is really read into the register AL, and the register AL means the low end of the register RAX. So after that, we can use, in the following, we'll explain how we use the side channel attack to read the value of RAX, so we can know what's the value of in a kernel address. And the question here is why Spectre and Meltdown can affect SGX. I think the most important reason is that these vulnerabilities are based on the features of CPUs, and the CPUs can see the unencrypted raw data. So this is the reason why such vulnerabilities is thought to can affect SGX. Okay, the story goes on, and now what we can do, with the Spectre and the Meltdown vulnerabilities, we can trick the CPU to execute some sensitive instructions and read some sensitive data and cause side effects inside CPU in its microarchitecture. But actually, we cannot read the value out of the CPUs. So how to read the side effects? So this is how the side channel attacks is used. Because there is no normal methods which can be used to read the side effects, because all it happens inside the CPUs. Okay, I have explained it before. And from outside the CPU, from our observation, there is nothing really happens, and only side channel attacks can do this. I will use a simple example to explain what is the side channel. For example, if we say people at home, it usually means higher electricity usage, because when you're at home, maybe you will watch TV, use your computer, and I don't know, do something others. And when people are awake, there should be lower electricity usage. But when we try to determine whether the people is at home or not, the director channel is that we can just peek through his window, and we can see, oh, whether the people is really at home. We can directly see it. But the side channel way is that we do not need to really peek through the window. We can just monitor his electricity usage. And if the electricity usage is higher than we say a benchmark, we can determine, okay, that the people is at home. Else we can say the people should be they observe its state. Instead, we use some byproduct or side channel information to infer it. This is what the side channel means. And the how side channel attack is used to read data from inside the CPUs, and it's also utilized. An important feature is that there is difference between the speed of data reading in different computer storage. For example, the CPU has its data cache, and we have the RAM, the memory, and then we have the disk, and even after the disk, we can have other import devices. And the reading space is the cache is much faster than the memory, and the memory is much faster than the disk. If you use the computer, you should know this. And also, the higher level of storage is often used as the cache for the lower level in computer. For example, when you try to read the data from the disk, your computer will first check the memory, whether your disk data has been loaded in the memory. If it has been read before, then it's directly returned, and it should be very fast. And in this case, we say there is a cache hit because the memory is used as the cache for the disk. And another case is that you have never read such files from the disk before, so there is no cache in your memory. So at this time, your computer will just read the data from the disk, and it first stored it in the memory for the future use. This is called the caching mechanism, and then it's returned to the CPU to process. And in such case, we can say there is a cache miss. And when cache miss happens, the time you need to read the same data should be longer than when the cache hit happens. So we can see such difference in the reading speed can be used as a side channel for us to infer the data the CPU is really used. And this is the idea. Actually, in real world, there are many ways to do the side channel attack, and the flush and the reload attack I introduced today is just one of the most simple methods in this area. And for example, the real world case that is the attacker can try to infer the encryption key using your AES encryption. And the AES encryption, it contains a called SBox. There is a lot of constants here, and all the AES algorithms use the same SBox. But when you try to use your encryption key, you actually access your SBox in different orders. So during your encryption progress. Okay, and the target of the attacker is to determine which numbers in the SBox is really used during your encryption process. And after the attack has known that, it can be great help for him to try to infer the real encryption key you are using, and try to decrypt your data. Actually, this is the steps of the flush and the reload attack. For example, I missed one. And the hint here is that each bytes of the SBox will be loaded into different slots of the CPU cache. The CPU cache has many slots. It's just like an array, I think. It's just like an array. So, and we really know the mapping between the bytes and the slot it is going to be stored. This can be known before all the things happen. Okay, so this is how the attack's going. first the attacker flush all the CPU's cache slots. It just evict it, and then it will let the CPUs to do the encryption work. And this process is not known by the attackers, because just let the user do it. And then the attacker will use an isolated process to try to infer what bytes in the SBox is really used by the users. And it's just based on the different speed. Actually, what the attacker is doing is that he used an isolated process to iteratively read each item in the SBox and time such process. And if the reading of 1 byte is very fast, we can know that the cache hit happens. And this why this can be fast, because the user process has used such items before, and this items has been used by the target programs. And so we can know, for example, the CA, during our experiment, the CA is read and we time it, we find the read of CA is really fast. So we can know, okay, the user process must have used the CA. Similarly, we can infer the other bytes in the SBox, which is used by the users, by the victims. And then such information can greatly reduce the exploration space of the attacker, and the attackers can infer your key in a short time. Okay, so I think this can explain the line 4 and line 5 of the attacker. And as explained before, the RCX can be read by because of the out of order execution to the register IX, and then the attacker used the IX as an index to access the RBX array. The RBX array is a probing array, and in such case, the register IX is actually encoded into an index of the RBX. Then the attacker just need to iterate it over the RBX array and see, okay, which element I read it, it's very fast. Then we can know the according index is the value of the RCX. Okay. After explanation, we can see that such side channel attack against Spectre and Meltdown is very tricky. And actually, there is many important prerequisites of the attackers to succeed. For example, the most basic requisite is that the vulnerabilities of Spectre and the Meltdown really exist in target CPU. Actually, there is no systematic research on the existence of such vulnerabilities in all the CPUs in the research, because we don't know the details inside the CPU. This is only known by the manufacturer. For example, the Intel, and all the security research do is that they try their best to get the as most CPUs as possible, and they just take it all of them as the black box and try it, and they report the vulnerabilities. So this is the first prerequisite. And the second request is that it can be only attacked locally, which means the process from the attacker need to be at the same machine of the victim process. This is also a very important prerequisite. So actually, we haven't, as far as I know, we haven't observed any attack case which is totally deployed remotely. This is very hard. You need to have a local process just near your victim, and this is the second prerequisite. And also there are other prerequisites. For example, there need to be attack controlled assembly snipped. This is always called gadgets in the security. For example, this is an example of the gadget. you need to have such gadgets on your target machine so for your attack to succeed. Also, you can use the existing ones if there really is. Also, you need to have a high resolution timer. This is important for such flush and reload attack and other attacks because you need to know you need a timer to tell you whether the cache hit or the cache miss happened. Also, such attacks is hard to succeed if it's just deployed only once. Actually, the attacker need to repeatedly deploy such attacks and gets the distribution of all the time to get the real accurate result. So the last prerequisite I think is the repeated probing request to the target programs. Okay, and Phala just try to tackle such prerequisites to protect our programs from the vulnerabilities of the Spectre and the Meltdown. And also there are other variants of Spectre and Meltdown, and also they can be defended in a similar way. First, as I have pointed out, not every CPU is vulnerable to the Spectre, Meltdown, and the other variants, and only Intel really knows which CPU is vulnerable. And so our according mitigation is that we only deploy the important infrastructure of Phala Network on safe CPUs. Yes, this is why we propose the confidential level of the miner. And actually, how we determine the confidential level of the miner? Actually, we just get the results from the Intel, because during your remote attestation process, the Intel will report the vulnerability status of your CPU model, and there is different status. For example, the software hardening needed, and also others. And for now, the most important infrastructure, for example, our gatekeeper, is only executed on the machine with the confidential level of tier 1 and 2. And to our best knowledge, such CPUs are free of the almost all known vulnerabilities. Okay, another request is the local attack request. And this means only our owners can apply the attack, because only he is locally access to the P runtime, right? And the mitigation is that first we apply random deployment, so the worker cannot control which contract to execute. And I think this is very important, because in this way, the workers cannot try to target any contracts executed in our network. Also, the network deployer can specify optional regular deployments of its smart contracts, so this can reduce the time for the attacker to infer their secrets. Okay, there is also other mitigations. For example, there are little assembly gadgets in our smart contract, because our smart contracts is compiled to the Watson binaries, and then the Watson binaries is executed by the Watson VM instead of just. So it's really hard for the attacker to try to get the real low level assembly gadgets, which is really executed. So it's hard for them to try to get such gadgets. And also, there are no high resolution timer in our P runtime. We do not support such operations. And third, in the smart contract cases, the repeated probing requests to the contract can be really expensive, because the commands have to be sent through the blockchain, which means the attacker he cannot send many commands in a short time and in a low price. Also, but it needs to be mentioned that our smart contract developer need to carefully design their queries, because the queries can be sent locally and in a very high frequency. But I think the query, since the query cannot change the state of your contract, and also the query will not you will not expose your important secrets in the queries, right? So I think this is not a very big problem. Also, you can check our media for more answers to these questions, because in our after the finish of each our tech talk, I will try to write, if necessary, I will try to write an answer to all the questions proposed by our listeners. So you can just check our Medium to my answers. Okay. Also, things need to be mentioned here is that about the responsible disclosure mechanism. Such mechanism is widely adopted by the research community. For example, if I reported any zero-day vulnerabilities in my paper and I submitted it to the conference or symposium, the paper reviewer will always ask you to do the responsible disclosure, which means you have to inform the author of the vulnerable programs and let him know about the vulnerabilities. And you can only publish the details of the zero-day vulnerabilities you find after the author have fixed such bugs. Also, the Phala Network, we have our own responsible disclosure and bug bounty programs, and we are willing to give good bounties to the important bugs and the vulnerabilities if any white hat find, and we are welcome for them to report them to us. Okay, this is all for today, and I will check on my questions. Okay, if you have any questions, you can just post it here and I will answer. Thank you, David. And if do Ryan, if you are actually there is no the hard limit of the maximum remote attestation cost which the Intel service can handle, but from our experience, the Intel service is sometimes unstable. It depends on its network qualities, and sometimes you cannot get the remote attestation reports. Okay, no more questions? Okay, if there are no more questions, I think this is all for today's talk, and it should be uploaded to the YouTube or finish it. Okay, right. Thank you. Thank you, everyone. Have a nice day.